Welcome to my channel, a number one channel for structural insight. In today's session, I want to talk about continuous L and T beam. And before I begin, I want to do a small recap on what we did in our previous session. If you can remember, in our previous session, I designed a singly reinforced beam and a doubly reinforced beam. So the beam that we dealt with, it was a simply supported beam. So a simply supported beam, it means it is a beam resting on two supports. This is a simply supported beam. So this is L, this is the loading, W over M. So to calculate the design ultimate moment M for a simply supported beam, it is very simple. You can use the formulas derived from the three equation of equilibrium. That is, the summation of vertical forces is equal to 0, the summation of moment about a point is equal to 0, and the summation of all horizontal forces is equal to 0. Then the formulas derived from that can help you to obtain the design ultimate moment for a simply supported beam. For example, this one is given by M is equal to W L square over 8. We have another case like this, a point load acting at the center of a simply supported beam. So this is L over 2, and this is W. So for this M is equal to WL over 4. We have also another case where the load is away from the center, eccentric loading. So this is W, this is A, this is B. So M is given by W A B over L. We have a cantilever like that. So for this one, M is equal to WL. So this is W. We have another one. So this is L, this is W over M. So M is equal to WL square over 2. So those are different cases for a simply supported beam. But it comes a time where the supports exceeds 2. It means you can have 3 supports, 4 support, 5 support, and 6 support, or even more. So how do you calculate design ultimate moment and shear force for such a case? So, for example, if you can look on the far end, this is a floor plan. So I will use to explain this continuous L and T beam using this floor plan, and then we'll tackle examples using this floor plan. So I will maintain it until we finish continuous L and T beam. So as you can see, this is a floor slab plan. These are the columns. These are the column. And this is the beam. These are the beams. So if you cut a section along this slab and beam, this is what you will have. So a T-beam, it supports both sides of a slab. As you can see, this is a T-beam. It supports on this side and also on this side. And L-beam supports on one side only, on one side of a slab. For example, if you can proceed to this plan, this is a beam. Let's call beam A2 and D2. So this one. So this beam, it is supporting this slab, a half of this and also a half of this. So we call it a T beam. So I was talking about the design ultimate moment M and the shear force V for continuous beam which has more than two supports. So we have a table, and this is table 3.5 of BS 8110. So this table, it provides us a formulas which help us to determine the design ultimate moment M and the shear force V. But there are a condition to be met for you to use such a table. So condition number 1, GK, which is a dead load, must be greater than QK, and the load should be substantially uniformly distributed over 3 or more supports. As you can see, here we have 1, 2, 3, 4 supports. So we have more than 2 supports. The last condition, spans are equal lengths or variation in span length should not exceed 15% of the longest span. As you can see, these are the span 8.5, 8.5, 8.5, 3.75, 3.75, etc. So those are the conditions that have to be met for you to use table 3.5 of BS 8110 to determine the design ultimate moment M and the shear force V. If the conditions are not met, then it means you have to use the normal way of beam analysis of continuous beam analysis, so that you can determine the maximum bending moment and the shear forces at various places. We have so many different formulas. We have moment distribution method. We have three moment theorem, or we call it the Klepperian theorem. We also have slope deflection method, etc. So I want to show you table 3.5 of BS 8110. So this is table 3.5 of BS 8110. As you can see, we have the end support, we have the end span, penultimate support, interior span, and the interior support. So for each case, we have moment and shear. For example, the end support, the moment is 0, and then shear is 0.45 F. So those are the formulas given in that table. So for you to use, you have to determine where the support is, maybe end support, or a penultimate support, or interior support, and also the spans. Then you apply the formula. Then F is equal to 1.4 GK plus 1.6 QK, and L is equal to effective span. So it means F is the design load. So you will see how we will be using it in examples that will follow after this. So generally, beams and slabs are cast monolithically. So monolithically, it means they are cast in a uniform pour. So the actual width of slab that act together with the beam is normally termed as the effective flange. So this is the effective flange from here to here. So clause 3.4.1.5 of BS 8110. This clause states that the effective flange should be taken as the lesser of the actual flange width. So this is the actual flange width, or B, the width plus LZ over 5. This is for T-beam, or LZ over 5 over 10. This one should be over 10. LZ over 10. So that one is for L beam, where LZ is equal to 0.7 times center to center support distance. So the center to center support can be a column to a column. So as you can see here, this is a column, this is a column. So center to center distance is 8.5 meters. The depth of the neutral axis in relation to the depth of the flange will influence the design process and must therefore be determined. The depth of the neutral axis x can be calculated using the equation 3.9 derived in section 3.91, and this is the formula: x is equal to d minus z over 0.45, where the neutral axis lies within the flange, which is normally the case. In practice, the beam can be designed as being singly reinforced, taking the breadth as effective flange width. And then, to moment reversal, B should be taken as width of the beam. So you will see this in our coming examples. So don't worry about it. You'll see how you will be applying in the question or when solving the question. So I will end there for today, and in my next session I will be tackling example 1 of T and L beam design to BS 8110, and subscribe so that you may be the first person to be notified when I upload a video. So thank you for your time. We meet again in my next session.